Swayam Prabha. Digital India. Educated India.
So, in the previous class, we started our discussion on modeling respiratory droplet cloud transport. Specifically, here our interest is to predict the trajectory of a droplet cloud ejected during human coughing process. And in particular, here we want to study the influence of the group evaporation phenomena on the results that we get. The group evaporation basically refers to collective evaporation of droplets in a cloud. So, they do not evaporate individually, rather they evaporate together. And in this case, we can expect the droplet vaporization rate to be smaller. So, this is characterized by this number called group number, which is basically a geometric parameter that depends on the particle size, number of particles within a cloud, and the inter-particle separation distance, the separation distance between particles, which is basically the refers to the volume loading, the local volume loading in the droplet cloud. And here we have some correction factor that accounts for the convective effect, as in the case of d square law. Okay, so I will go little bit detail into this modeling approach. This is to give you a flavor of how do we model a physical phenomena, and how can we validate the results at appropriate places against simulation and experiments. So, the first step here is to develop the physical model first of all. So, here we consider droplets ejected into atmosphere, which basically has air. And here we are neglecting any kind of atomization or primary or secondary liquid breakup of the liquid outside the mouth. Okay. So, here the assumption is that there is direct droplet generation right from the mouth, and those droplets do not undergo further breakup, that is the point. Then here we assume that all the droplets are ejected with the same initial velocity. The initial velocity of all droplets are same, though here this is not a strict restriction. This can be accounted also in your model. Then here we have a co-flow of air past a human being, and here we assume that the flow velocity is spatially uniform and also it is steady. So, when I say flow, here I am referring to air flow. So, the air flow velocity is steady as well as it is spatially uniform everywhere, and this we can vary. So, this u infinity is equal to 0 refers to droplet injection into stagnant ambient conditions. Then we can assume that the mouth injection area, so which is similar to a rectangle. So, here we simplify the scenario, okay. Though this is also not a restriction, we can account for any shape. Also, we can account for the change in the shape of the mouth area with respect to time. For simplicity, here we are assuming that here the droplets are injected from a rectangular region whose dimensions are similar to a typical mouth area. Then the height is considered as a typical height of a human being. Then the droplets which are injected, they are assumed to follow Rosen-Ramlet distribution. So, as you know, this requires some inputs, that is spread parameter and the scale parameter, and these values we get from some experiments. So, people who have done experiments and they have measured size in actual coughing condition. So, we get this information from them. So, a typical value of scale parameter here is assumed as 85 micron, scale parameter is 3, such that this distribution fits to a experimental size distribution, and the size range is this. And there are some other parameters also which we need to consider, that includes the mass of injection of droplets, how much mass of droplets are injected in one coughing event. This is also taken from some experimental data. Then injection duration, this is also important, how long the droplet injection or the coughing process to be considered. Then characteristic droplet size, which I have already shown. Then droplet velocity, typical velocity that people have measured, that is what we have considered. This is the initial injection velocity. And droplet temperature is 34 degrees centigrade, corresponding to the body temperature. So, here you can see schematic of the physical model here. Next, these are the conditions. So, we can do this analysis for various conditions where we can vary the surrounding temperature, the relative humidity, and also the air velocity around the human being. Okay. So, you can see a large number of analysis we can do. Next, governing equations. Governing equations, what we have already discussed. So, the momentum equation, and this is the equation for trajectory, particle trajectory. For this you need the velocity which you get from the momentum equation, and we have appropriate correction factors here. Then the mass conservation equation, here we have the d square law along with the convective effect, and also from energy equation we have a rate of change of temperature of a particle, that also we can consider. And here this is the heat flux which depends on the mass flux, which is given in terms of the evaporation constant. And these equations are for a single particle, but in our case we have a polydispersed system, but the equations remain same. What will change is the size only. Okay. So, basically we have to solve this equation for particles of different size. Okay. So, if you remember, I have earlier discussed how do we get the number of particles for each size, because we know the mass flow rate of the droplets. We can calculate the number of particles injected per unit time, and because we know the probability distribution, we know how many number of particles of a particular size are injected. So, that information we have. So, here the results are shown for the basic droplet transport process. Basic process means here we have not considered any group evaporation effect. Okay. So, what happens as the particle cloud is injected? So, here two examples are given. First one, where the particles are injected under ambient condition, stagnant ambient condition. Second one, where there is some co-flow. So, here what do you see? For example, here 120 millisecond after the particles are injected. So, you see that the large particles are leading the cloud, smaller particles are lagging behind, okay, which is expected. This is according to the particle relaxation time. The large particles tend to adjust with the surrounding flow, which is at zero velocity, but the larger particles are moving ahead. And here you see that because of gravity, the particles tend to settle down. So, obviously, the larger particles will settle earlier. Now, when we have the co-flow, here you see that the topology of the particle cloud has changed. What you see here is basically a flat front. Why is this so? Why we did not see this in this case? This is mainly because of the Stokes number. So, what would happen to Stokes number of the particle as you go from this case to this case? So, Stokes number is basically the particle relaxation time to time scale of the flow. Now, what happens to the flow time scale if you have some finite velocity of the carrier phase flow? What do you expect? The flow time scale would tend to reduce, because if we define let us say the flow time scale by say this represents the characteristic length of the mouth area divided by u infinity. So, this gives you the flow time scale. Okay. So, under stagnant condition, this time scale is basically very large, but as the airflow velocity increases, the time scale reduces. So, this parameter basically reduces. So, the flow time scale is now smaller. Okay. And here in this case, we see that the wait a moment. So, yeah, so flow time scale is smaller, though it's we can calculate the time scale also for the stagnant case by considering some time scale of the flow by considering, let us say, considering the droplet velocity instead of the air velocity. But here we have calculated Stokes number for this case, and in this case you see that Stokes number varies in this range. So, this is mostly below 1, though this is also close to 1. So, what does this mean? This means that the particles are responding well to the surrounding flow. So, what happens in this case is that the particles quickly adjust to the surrounding flow, such that mostly particles are having similar distance traveled at a given instant of time. And also we can check this by considering the theoretical analysis that we did earlier, where you inject one single particle and you calculated what is the distance traveled by the time the particle reaches say 99% of the velocity. So, velocity of the carrier phase flow. So, in this case it is possible to show that the distance, the final distance between particles of different size is more or less similar. So, all particles are reaching the velocity equal to the co-flow velocity soon. So, that is why you see this flat front. Okay. Now, but you may wonder, if the particles really behave like this, do you really expect a flat front like this or such a organized topology of the particle cloud? The answer is no. So, if you remember, I had shown you a photograph of a person coughing some time earlier. So, there we see that the particles spread in all directions. So, here we do not see that. Why? This is obvious because we did not consider the turbulence in the particle. Okay. Sorry, turbulence in the airflow. Okay. So, that is why there is no as such dispersion of the particles. Okay. So, how important it is to consider the particle, the fluid turbulence. Okay. Next question also is, here if you see in this model, we are assuming that only particles are injected from the mouth. But in reality, along with particle, gas is also injected, which is different from this co-flow that we have considered. But if you want to model that, it will become more complex obviously, because here you have a jet of gas which is injected, which tend to mix with the surrounding flow. So, you have to solve the carrier phase flow equation, okay, and you need to obtain the flow field and then consider the particle transport. We have not done that. Okay. Anyway, now that is what we will discuss now. What is the effect of air turbulence and initial gas injection? So, to compare the results, we have performed three-dimensional multi-phase numerical simulation of droplet transport process using ANSYS Fluent. So, in this case, see these numerical techniques, the details of it we will discuss sometime later in the course. But here I brought in because the purpose here is to see how important are these effects and how well the predictions from the model agrees with this simulation. So, here basically in short, the gas phase equations were solved in a Eulerian framework, while the particle equations were solved in a Lagrangian framework using discrete phase model or DPM model. We will discuss all this later. And in the simulation also we have not considered the group effect, because here the main objective is to assess the influence of gas injection and air turbulence, which are not accounted in the model also. So, because we have not considered that in the model, so in the simulation also that was not considered. So, now here you see this shows the axial distance travelled by the cloud, the droplet cloud, with respect to time. Here there are no model results. Here we are only comparing the simulations for the case where we have 1% turbulence in the air and 10% turbulence, and also when we have initial gas velocity also, that is the gas which is injected along with the droplets, that also we have considered. So, finally, what we see here is that neglecting the gas injection and air turbulence in the model can lead to some difference in the droplet trajectory, obviously. But this is mostly, this may be mostly important for the stagnant ambient case, while for the co-flowing case there is no difference. And also here you can see the difference is not significant. Okay. So, this means that our assumption of neglecting these effects is valid up to some extent. Okay. Next, if we look at the result, the comparison between simulation and the model, we get the results here. So, here also you see that as far as the axial distance travelled by the droplet are concerned, and also the time evolution of droplet size is concerned, the model agrees well with the simulation. Okay. However, here we are not concluding that the model can always replace the simulation or experiment. It depends on what is the objective. If the objective is to find the final distance travelled by the droplets, then yes, the model seems to be working good. But if we are interested in, let us say, the dispersion of the particles, okay, in cross stream direction, the particles are also dispersing in the other directions. So, if we are interested in that, then it is difficult to account for that in the model. Okay. Now the next question is, how do we model now the group effect, which is also a key objective of this exercise. So for that we are invoking a model proposed by Sirignano. So there is some overlapping here. So here what they have done is that they developed a theoretical model by considering a three-dimensional array of droplets, which means you imagine you have droplets which are regularly spaced in a three-dimensional array. So by solving the transport equations, they came up with a model that accounts for the neighboring droplet effect. That is, when we have two or more droplets nearby, then how the evaporation rate of the droplets are affected. Okay. So this they could bring in this effect through a simple form. Here you may not be able to see it. So they have introduced a correction factor to d square law basically. So this is the correction factor eta g, and which is given by this expression, which basically depends again on the number of droplets we have in the cloud and the interdroplet distance and the size of the cloud also. So this is one model. So in this case, if this parameter eta tends to 1, this implies that you are approaching the d square law, that is, the particles are far apart, so that d square law is valid. But if it tends to 0, this means that the group effect is considerable. So now we can calculate this parameter in our model because we know the droplet cloud. Okay. Next, there is also another model where these authors have considered droplet evaporation rate by fitting, by doing appropriate fit to experimental data obtained by considering simultaneous vaporization of water droplets stacked on neighboring threads. So they have, you can imagine, they have many threads, okay, and they have suspended droplets, and they somehow measure the evaporation rate of the droplet. And so this is basically an empirical correlation you can see obtained from experiment. So we have these two models. So now the question is, how do we implement this in our case? So this can be implemented because in this case you know how particle size changes with time directly, and in this case we have this correction factor which can be calculated from the geometry of the droplet cloud. Okay, but before that we wanted to know how well these models perform against experiments, because here we do not have experimental data, we are doing theoretical modeling. So for this purpose these experiments were conducted. So here you see we have a single droplet, here we have dual, and here it's a triple droplet case. And by imaging these droplets, and we can calculate how the droplet size vary with time in experiment, and then we compare that with the with different models. Okay. So here you can see that we have very good agreement, especially with model 1, while model 2, which is shown by the red line, agrees well when we have very small separation distance. Okay. So now we can proceed to implement these models in our theoretical model and calculate this parameter eta, which represents basically the evaporation rate in actual case to, this is the ratio of evaporation rate of a droplet in a cloud to the evaporation rate in an isolated droplet. So that is the reason why if this parameter tends to 1, then we have d square law valid basically. Otherwise, this correction is required. So, now we want to know, once we inject this droplet cloud, then what happens to this parameter, and this is what is shown here. So, here you see that initially this parameter is really small, that is it is around 0.1, then it decreases and then it starts to increase for all cases. Why? This is because initially the droplets are closely spaced and then they are dispersed. Okay, in our case, we do not see dispersion which is expected in an experiment, but still the particle cloud, the area, effective area increases and the separation distance between particles increases. So, that is why this increases. Accordingly, if you see this group number, this one increases and then decreases. So, this follows nearly this trend. This is nearly opposite to this trend. Okay. So, when this parameter is very small, the group number is high, indicating that for this case the grouping effect is high. But after that, the group number tends to 0. So, indicating that towards end of the transport process, the droplets are kind of, they are far apart, so that d square law is valid. Now, here you can see how the co-flow also affects this behavior. Okay, so now here we want to know what is the real role of this group effect for the cloud transport. So, if we consider a single particle, single droplet, then this is the droplet evolution with respect to time when we do not have group evaporation. So, as expected, if we implement the group evaporation model, so here when I say model, here we are considering only the first model. So, you see that the particle size is now larger because they are evaporating slowly. And now the question is how that affects the final particle trajectory and or the final distance traveled. So, here you can see, for interestingly what we see is that for stagnant case, they are quite close to each other. So, this is in log scale. For stagnant case, they are quite close to each other, but once we have some co-flow of air, large difference can be found. And according to this model, what we see is that this difference can be about 4 meter and 16 meter when air velocity increases from 4 to 15 kilometer per hour. This is the difference. What I mean is that if you consider d square law only d square law model, and then you account for the group evaporation effect, you see that the particles are transported a longer distance. Okay. And when we have co-flow velocity say 4 kilometer per hour, we have the difference of 4 meter and it can be 16 meter also. Okay. So, this means that a gentle airflow can cause deviation in this norm of 2 meter safety distance. Okay. Yes, so one has to validate these results with experiments. Okay. So, experimental validation we haven't done, okay. But still it gives you a very good idea of a quantitative picture of what would happen when we change the key parameters. And once you have the model in place, we can do various parametric studies. For example, here we have varied the injection mass. Now you change the injection mass, because all we have considered as of now typical values, but depending on the particular depending on the human being and the infection rate of infection, how much infected a person is, these values can change. So, now we can change this and see how the group effect is important. So, for example, here the injection mass could be changed, then injection duration, initial droplet size, everything you can change and see the what range of group number we are getting, and how the droplet trajectory is affected. So, for example, here we see that variation in droplet size for the same injection mass leads to a stronger group effect. So, basically the variation in size significantly affects the group evaporation effect compared to the injection duration or mass of injection. Similarly, we can consider the effect of ambient temperature and relative humidity also. So, for example, here you see all the three black lines. So, which are done for the same ambient temperature, but you increase the relative humidity. So, if the relative humidity is higher, what would happen to the evaporation rate? It will reduce, because the concentration gradient between the vapor between the droplet surface and surrounding would reduce. So, this is expected, but we get a quantitative picture here. So, similarly, if you increase now the temperature, then the droplet evaporation rate would increase. And here we have calculated the suspension time also. So, you can see how long the droplets suspend, okay. That also you can calculate. So, the whole idea here was to introduce you to the modeling approach, that how the modeling approach should be taken, what kind of simplification we can introduce initially, and how do we compare the results wherever necessary to experiments or simulations. So, then one can ask, okay, why do not we do experiments and simulation? What is the necessity of the theoretical model if you can do experiment and simulation? The answer is, first of all, as far as simulations are concerned, it is always the cost part always comes into picture. Okay. If you can do a theoretical analysis and you can calculate the parameters which are necessary. For example, let us say in this case, here our interest is on the axial distance, basically how long the droplets would transport. If that is the objective, then it seems that the model can be fairly accurate. Okay. Or let us say, if what is the suspension time. Okay. So, at least I can say that it gives us a first hand estimate of these quantities. So, it will help further simulations. So, you can reduce the number of simulations that you need to do. Similarly, conducting experiments for all cases are not possible. Okay. So, for example, to track individual particles when a human being coughs is very difficult, okay, apart from the fact that there are safety issues. But even if you take care those issues, tracking individual particles to see their behavior, for example, group effect, okay, it can be done, but there are some limitations too. Next example is on a completely different problem. Okay. So, here we have basically particles or solid particles. We deal with solid particles in liquid flows. So, this device is called lamella separator, which is used for water treatment. So, basically it is a gravity driven technique to filter out suspended heavier particles from water. The idea is simple, that is, you have a channel here which is at some inclination, and water enters the channel, the water carries particles, the particles settle due to gravity. Okay. Now, the particles settle and you have this sediment formation here, while the clean water leaves from the top. So, this is the overall idea. So, here the what are the specifications given to us? They are: mass flow rate of water is known. You know the particle loading ratio, that is the ratio of the particle mass flux to the mass flux of the fluid or the carrier phase. But in this case, because the area is same, so this translates to the ratio of mass flow rate of particles to mass flow rate of the water. Okay. And this is the global value. This is not local, this is global. And we know the channel height, we know the depth. The depth of the channel perpendicular to the plane of paper is much longer than the channel height. Okay. So, at the channel entry, we know the characteristic particle size also, and here we can assume that the initial velocity of the particles are same as that of the liquid. Okay. So, now what is the objective here? What is the problem statement here? The problem statement is that we need to find the minimum channel length and minimum time duration required for settling of all particles in the channel. And we need also to estimate the sedimentation rate of particles, which refers to the rate at which particles settle at the bottom of the channel. Okay. So, the question is, how do we approach this? How do we develop the physical model? So, here we consider the schematic again. So, here first we need to solve only single particle transport. Why? Why we need only single particle transport? As far as the distance is concerned. Okay. So, this is because the particle which is at the top of the channel, it will take longer time or longest time to settle, considering that they all enter at the same velocity. So, we can consider the single particle equation for the particle which is here. Okay. Then we have to select the coordinate system appropriately to simplify the analysis. Okay. So, if we choose the coordinate system like this here, the analysis will become very simple. So, then you consider each particle. So, this is basically the velocity in the axial direction. Actually, this should be Vx, and here you have velocity in the cross stream direction also. So, now we have different components of acceleration due to gravity in both directions. So, now the gravitational term will appear in both momentum equations. Then we can assume fully developed laminar flow of the liquid. Then we can neglect the volume of particles deposited on the wall. This is again to simplify the analysis, such that the effective area, we can assume that it remains same, otherwise this area will change. And here the other assumption is that we have only one-way coupling. That is, what is one-way coupling? That is, only the carrier phase influences the transport of the particles. So, only the particle equations need to be solved. That also, here we need only the momentum equation. Okay. So, how do we start? So, first we need to calculate the liquid velocity first of all. Okay. So, we know the mass flow rate. Okay. So, from there we need to calculate the liquid velocity. but for that we need the bulk density of the carrier phase. So, how do we get the bulk density of the carrier phase? So, we have the particle mass loading ratio, and here because we have assumed that the particle velocity and the carrier phase velocity are similar. So, this is basically equal to the concentration. Concentration is nothing but the ratio of the bulk density of the particle phase to carrier phase, which we can write in terms of volume fraction this way. And finally, we have only one variable, that is the volume fraction. So, once you know the volume fraction of the particles, you can calculate the volume fraction of the carrier phase, and then you can calculate the bulk density, and from there you obtain the velocity in the axial direction. And here in our case, we have velocity only in the axial direction. Okay. Then we can calculate the particle mass, particle injection rate in the same way as we did earlier from the mass flow rate of the particle. Because we know the particle loading ratio, we can calculate the mass flow rate of the particle, and from there the injection rate can be calculated. Also here we have assumed monodispersity for simplicity. Okay. So, all particles are of same size. So, you can calculate the particle injection rate. Then the equations. So, here we considered the x and y momentum equation. So, in the x momentum equation now we have one we have a term involving component of the acceleration due to gravity, and in y momentum equation this velocity is 0. So, and we also have component of the acceleration due to gravity. So, by solving this we can calculate the trajectory of the particle. Okay. And then the time required for the particle to reach the bottom plate can also be calculated, and also this will give the length, the minimum length required to for settling of all particles. So, we will do this in the next class.